Field due to, so potential due to shell. Now first, let me pick up a point which is for your convenient, I'm writing where the mass is present. Only the green color is a spherical mass, spherically distributed. So this will be at a distance. So first, what happened? The point R greater than capital R, VP1 or V out. Find out the field strength at point P1. Again, the idea is same. If you draw a Gaussian surface, the whole mass will appear to be where? Concentrated at the point mass. It appears to be point mass placed at the center of Gaussian surface. So what is this one? This should be equal to minus Gm by R. Potential on the surface. Look at clearly. Same thing like previously what we did Gaussian surface, we have to do it. Okay, let's come for the point inside now. Let me come to the last point inside. So where is the point P3? Point P3 lies inside the spherical surface. What is the field strength inside? What is the field strength inside? First we'll look at the field inside the shell. Should be 0. I think we have discussed this also. The field inside the shell will be 0. Any reason for that? What is the net mass enclosed by the Gaussian surface? Will be 0, no? But sir, like can't this contribute? Already we have said like the net mass enclosed by the Gaussian surface is 0. So therefore, no field at point P3. Net field at point P3 will be 0. I'm saying net field at point P3 will be 0. Simplest way using Gauss law. No mass is enclosed. Or else, so what is the thing? So at this particular point, what these elements, so you can take like this. So how much this cap will contribute, equal and opposite that this cap will contribute. So like that, open the net field at point P3 will become 0. The field is 0, then what will happen to potential? So you take help of this basic formula. E equal to dV by dr. If E is 0, for E to be 0, what should be the value of V? Should be constant, no? Differentiation of constant only will become 0. Go back to mathematics. So what you can say about now V? V must be constant. If V is a constant, then only E can be 0. So what happened to the potential inside the shell? It will be constant at all points. But how much, sir? Okay, constant, we know how much. Then you do one thing. What we know potential on the shell, on the surface. So what is the potential on the surface? That will be the potential everywhere inside this one. So we use formula like this. EP3 equal to minus delta V by delta R. This is equal to 0. Delta V, potential on the surface minus potential at point P3. This should be equal to 0. Anything what all you can write. This will be R minus small r. Anything multiplied with 0 will be 0. So finally what we are getting, potential at point is equal to this one. What is the potential on the surface? It's a simple idea. What is the potential on the surface? That will be the potential at all points. This one. At all points inside the shell. See, it's quite, I think, rather than troubling with this side, no? So better come for this one. For E, 0 means what? When V should be constant. So delta V should be 0. Delta V to be 0 means potential difference should be 0 between any 2 points. I'll take between these 2 points. Potential difference is 0. So we know potentially here how much? Minus Gm by R. So therefore the potential at this point also should be minus Gm by R. So what is the potential? So don't take potential at O. We don't know this. We know only on the surface. So therefore I'm taking here. So what is the potential inside the shell? Will be constant. Don't say 0, will be constant. How much? Equal to that on the surface. I think this is something very important. This also you can call V in, VP3, no? So just make it a very generalized one. So shall we conclude here? Potential and is equal to that on surface. This is all the information. So rather than saying concept, according to me, they are all just information. You must know when you get into the numerical. Let's take some questions on this.